So we have this fairly simple RT function. We want to find velocity, tangent, unit tangent, so forth. Always a good idea to start graphing the thing. But the graph is a little more complicated because we've got this 2t on the sine function, which means the sine function goes through a complete cycle twice as fast as the cosine. Okay, so you could kind of almost think polar coordinates here. If t equals 0, you're at the point 1, 0. If t equals pi over 2, then the cosine is 0, but the sine is also 0. The sine of pi is 0, cosine of pi over 2 is 0. So you go from this point to this point while t goes from 0 to pi over 2. Okay? And what happens? Well, the cosine starts decreasing, the sine increases, but then it decreases again. So the graph, without going into detail, because we can always analyze the graph, finding degree points and stuff like that. But we're not going to analyze it to that extent. We're going to do something like this. Maybe it's an arc of a circle. It's probably symmetric. Maybe it's circular, maybe it isn't. Okay. And you could, if it's circular, then the center is at 1/2 0. And you could take the distance from the 1/2 0 point to this point here and see if that distance is always 1 or 1/2. Okay. I tend to think it's not a circle, but it's 1/2, but I just check it out. Okay. Now, as t then continues, the cosine goes negative and the sine goes negative, right? Because cosine past pi over 2 becomes negative. Just look at the unit circle here to the left of the y-axis. And you're talking about the sine of argument that goes from pi to 2 pi. So the sine again goes through a complete cycle, but it's negative throughout that cycle. So both the cosine and the sine are going to be negative, and that's going to give you this kind of a reflection through the origin that you have here. Okay. And something's wrong with that. No, cosine stays negative. Okay, this is at t equals 0. This is at t equals pi over 2. And this is at t equals pi. Okay. Then the cosine is going to stay negative, but the sine is going to become positive. Well, you do symmetry tests. I think do the symmetry test. The whole thing's going to kind of look like this. Maybe it's two circles, maybe they're deformed. Okay, you can test that very easily. Okay, just by saying if it's a circle, then your center is here at 1/2, 1/2. So what's the distance from 1/2, 1/2 to cosine t, sine 2? Okay, it's going to be cosine t minus 1/2, sine of 2t minus 1/2. Square those and them up, see if you get an idea of the probably. Some days I can do that in my head, but okay. So it's a, you know, just by thinking what happens as t goes from 0 to pi over 2 and so forth, you can kind of reason out this shape. I don't even guarantee I did it right, but it seems like it. Okay. Check it yourself. Okay, so anyhow, the force is the r dt, which is negative sine of t I plus 2 cosine of 2t. Okay. The tangent vector is in the direction of the velocity, but it's got to be the unit vector. This equal to the velocity vector over the magnitude of the velocity vector. Now here's the velocity vector. sine squared of t plus 4 cosine squared of t. Okay. ALT stands for alternatively the square root of plus 3 cosine squared of t. Since a sine squared plus one of these cosine squareds gives you 1. Right? Yeah, it worked if what I wrote down there was correct. This is cosine squared of 2t, so forget what I just said. Okay. If it was a cosine squared of t, you could do that. And that occurred to me, and didn't occur to me to write it out correctly. Okay. Okay, so there you have unit tangent, the familiar acceleration vector. Whether as derivative of velocity or second derivative of your position is going to come out negative cosine of t times I. And then you're going to have minus a sine of 2t. Okay, I believe. Not a mistake. I doubled too many times minus. Double that, so double this. Okay. Makes sense? Is that what you got? Everybody okay with that? Okay, there's your acceleration. Well, your acceleration vector parallel. First of all, this is right, typical velocity vector. This point, like you like. Well, acceleration vector. Is this thing speeding up or slowing down at that point? Cosine is decreasing. Sine is negative. Magnitude, of course, is that point. Sine is going to be increasing faster than cosine is decreasing. So I'm going to assume, without really knowing, maybe the acceleration vector is plus one. Okay. Then there's velocity and acceleration vector. Picture what you want is velocity, acceleration vector. Right here is your A parallel. And I asked for the vector A parallel. And okay, here's A. Here's A perpendicular. Okay. Now this could be the velocity vector, or if you want the unit tangent vector. A parallel equals acceleration dotted with a unit tangent vector. Okay. And then that's multiplied by the unit tangent vector. They did have an arrow over this A perpendicular. Okay. So if you just got the magnitude, that's okay, but you multiply it by the unit tangent vector and you get a vector of that magnitude. Since the unit tangent vector is a unit vector. And you want to make sure that if you take the dot product of any vector with a unit vector, you're going to get the component of that vector in the direction of the unit vector. Okay. make sure you understand why that is. Case A dot T, that I'm not gonna write out details. A dot T is a cosine of T times this, right? Negative cosine of T times. It's gonna be dot product, this with this. I'm just gonna write the denominator because it just goes along with the whole thing. And then if I do the J component times the J component, we're gonna get a -8 sine cosine. But it's sine of 2t times cosine of 2. Now you can use double angle formulas and stuff like that to simplify this in terms of sines and cosines, and normally maybe you would do that so you can see more about the structure of it. And right now we're just talking about, okay, how do you calculate it? Here it is. There's some simplification that might take place if you use your double angle formulas for the sine and cosine. Then we ask for a perpendicular. Now, this point, you know, things you kind of covered. So calling it a perpendicular is a minus a parallel. So there's a dot product of the derivative time dotted with dotted dot the derivative, the second derivative, and divide that by the magnitude of one of the two. Okay, it gives you a magnitude, doesn't give you a vector. Okay, but there's probably something in that formula that gives you a vector. I prefer just to stay geometric on this, but that formula is fine. If you want to use that formula, you can use it, but you should see that a perpendicular is a minus a parallel. It's because a parallel added to a perpendicular equals a. These vectors are perpendicular. These are the components. You add the two components, vector components, and you get the vector. Want to be comfortable with that, okay? And you need a common denominator to add the two, okay? And the whole thing would get pretty complicated and wouldn't have a lot of meaning unless you analyze it a little more deeply than we want to do right now, okay? And of course you can do that, but there's your a perpendicular. So your normal vector the a perpendicular over the magnitude of a perpendicular, or a formula that I'll explain later if you want to see it, okay? But geometrically and logically, that's what's calculated. Now, it's going to be a pretty messy thing. Magnitude of a perpendicular. To get a perpendicular, you're going to have to subtract this from this, okay? Again, different denominators and stuff. It's going to take you a half a page. It's involved. But that's how you get the normal vector. So then your binormal is equal. And that's going to be a loss. So I looked at it before I had a chance to finish it because it's so hairy. I wanted to give you about 15 minutes, which is, you might have taken 20, but it was good to just get your hands on it. If you do that, then you're in fairly good shape with this stuff. Now, you did ask last time about what's the matter with this thing. I need to look at the screen every once in a while, but I just get so excited. Okay. it was zoomed back a little bit, but I think I wrote more neatly than you. Also comment, the video I did Tuesday. Anybody watch that video? Anybody hear everything? Microphone is, I think, malfunctioning. I've switched to the microphone on the computer, which isn't as good as that Logitech microphone. Logitech microphone's been through COVID and everything. I mean, might have picked up a virus. Might not even be that. It might be the docking station. So I've bypassed the docking station and everything. This gives adequate audio. And when I have time, I'll try to locate a better microphone to give better audio, because some of the transcripts and stuff come out better with a better microphone, but there's only a marginal difference between the two. So I think things should be okay. I'm crossing my fingers. I did another video on that. It's posted on the site, so if you want to see it, it's about 2/3 as long, and I go over everything because I had the report. I did that a day or two later. I was going to talk about quadrant surfaces for a minute. So remind me to come back to that. They did have a couple of little errors. Right there's the second thing I did in class on Tuesday. I did put my primes. Okay. So as I was explaining it, I said, okay, here it is. And it's like that. Wait, where are the primes? Okay. So this is the reason why this is, but this wasn't right. But this was, okay. And then I fixed this. That's the only real mistake. And then I had a 1+ here for a while, but we talked about that last time. That's just to go back to the formula for a function f of t, 1 plus f of t squared. So I just wrote the 1 without thinking. And I was going to draw an analogy with that, but decided, no, I'll just go with this. And then it's a little brain freeze. Put a 1. Okay. Which I know better at. So, okay, so we have that. And since I'm talking about what we did on Tuesday, the record, we have tips on it. But when they wrote so. Okay, is that all on the screen? Don't think we've got all of it. Okay, there's everything on that side of the screen. And I've got a couple of things over here that really are relevant to what we're going to talk about starting chapter 4. Okay. Main thing is this picture, which relates directly to what I just did. Just went through the calculation. Pretty simple function. But even for a simple function, those calculations get pretty hairy. That's life. Things don't get too much hairier than that. And if they do, you should know how to do it. It's just logarithms, algebra. But boy, you get a lot of opportunities to make mistakes. Very easy to move on. So I just pretty much did this, but there it is. And over here, talking about vector value functions, where we're headed x and a y, so we have 2 variables. And that's what we're getting into in chapter 4. Okay, so you can just kind of think about what we did here. We're going to do more of it. The first section of chapter 4, which is all I'm going to assign for Thursday, I think is pretty easy. Okay. Doesn't stay that way. It's pretty complicated. Okay, so I think that available. And this. Okay. Yeah, quadrant surfaces. Just think of parabola x squared over 9 meaning plus z squared over equals 4. Okay. Axis intercepts on the x-axis are at 3, -3, right? If we have axis intercepts. In the xz plane, we do have intercepts at 3 and -3. Because in this xz plane, we have an ellipse, right? Semi-major axis 3, semi-minor axis of 2. So just a simple ellipse. I don't want to draw that. I drew some of these things, first picture I made, and that's not the best way to construct it. I wanted to show you a little more. Depends, you know, it depends which is better for you or me or whoever. Okay, now, whether we actually have a y-intercept or not, and I would go with not because this is automatically negative. And well, actually, never mind. Yeah. Okay, anyhow, we got y equals 4, y equals -4. Then we got z equals 2, and z equals -2. So that very likely. This rectangle in the XY plane, and the way you draw that rectangle is you just make sure you go through all these intercepts and keep your sides parallel to the axis, right? So this side has to be parallel to the x-axis. So if that's done on the XY plane. In the XZ plane, we could draw another rectangle. And like so. Okay, can you kind of see that this is in the XZ plane and this is in the XY plane? And then to complicate it still more, we can sketch the YZ plane, which is a whole lot like the XY plane. But this is actually going to look like a rectangle. Something like this. So there are 3 rectangles. Okay. In the XZ rectangle, we could draw an ellipse. And maybe we will. Okay. In the XY plane, we have an ellipse. X squared minus y squared equals 1. Okay. So y could equal 0, it would be fine. But if x equals 0, you'd have a negative equal to 1, and it can't be. Okay, so x is not going to be 0 on the graph. So you're going to have a vertex and y is plus or minus 4, right? So that would be here or here in the xy plane. And then your hyperbola would open back this way and back this way. Okay. So I could draw the 2 diagonal lines here and here, and then sketch the full corners of hyperbola. So it would look like in the XY plane. Well, y would be here, here, here to hyperbola. Make sense? If it doesn't, because I was looking at it wrong. And this would have x equals 0, which would make the y squared over 16. Well, that would be negative and could equal 1, so actually vertex is over. Yeah, I was just looking at it. Just confused my orientation when I looked at this. I treat this like the x, and that's the way I gestured it. So actually, you have the x-intercept where x equals 3 and y and 0 goes 0. So it's here, and it comes out this way and back that way. Okay. In the YZ plane, it's the analogous thing, except you can have y equals 0, so you're going to have a hyperbola in this plane. Okay, opening upward and down. All right, that's a lot to visualize, especially if you're not used to looking at these things. In order to sketch this, sketch it in planes parallel to the coordinate points. Okay. If I choose, as I go Will Street, so sketch this. This is horizontal planes with hyperbolas. Because Z increases, X is going to have to get bigger. It's going to become inconvenient. What I'm going to do is vertical plane, the XZ plane. So in the XZ plane, one thing we know is we get an ellipse. That looks something like this. And there's I'll skip vertical lines here to indicate that it's improving. Okay. Now this is in the plane. Zero. In the plane, y equals 4. Why would I go to the plane y equals 4? Well, it's because y squared over 16 would be a only. Okay. Y squared over 16 would be 1. We'd add 1 to both sides. Now our ellipse would be x squared over 9 plus z squared over 4 equals 2. We divide by 2, which gives us x squared over you could rearrange this and get this very simple. Okay, whether you see it or not, just think about it. I just divide both sides by 2, and then I took the square root to get the major and minor axis. So the major axis is going to increase by a factor of square root of 2, about 1.4, almost half again as big. And so is the minor axis, right? So if I come to the y equals 4 plane or the y equals -4 plane, I have to draw, and let me, in just a second. Sketch this rectangle in blue. I'm gonna have to sketch another rectangle in blue and the plane where y equals 4. It is gonna have to be 40% longer and 40% higher, because square root of 2 is about 40% more than 1. So instead of 3, we have 3 square root of 2, which is roughly 4.2. Okay. Uh, but 3 times 1.4, yeah, it's 4.2. Okay. Whereas before it was 3. Okay, so I gotta come out here. This way to draw it is draw it out. Okay. So first I'm gonna take this line and extend it 40% further. Okay, that's the line in the XY plane that was originally going from -3 to 3. Now it's going from like -4.2 to 4.2. So it's gonna get there. Okay. In this dimension, well, this dimension is going to get 40% bigger. This dimension is 2, going to become about 2.8, almost 3. So it's like we got a new X and Y axis here. That's our X and Z axis. And I can sketch a new rectangle bigger than this one. Let's put it over the X axis. It comes over through like, okay. You can kind of see where that rectangle is if you understand it. Okay. Didn't do it quite right, but you get the idea that you're getting a bigger ellipse. If part of it's hidden by this ellipse. It's about twice the size, because it's about square root of 2 times as long and square root of 2 times as wide. Okay. So there's a new ellipse. So you got this ellipse sitting here and this ellipse sitting here. And you'll have a similar ellipse in a center here. So it's going to kind of go. So then like so down here. It's going to be big. It's going to hide part of this ellipse, but it's going to come out to here. Okay, so you're going to have a part of it that, where is it? Lose my lines. So that one's almost going to be outside. So but anyhow, it's going to be kind of back here. It's going to continue around. But I don't want to draw the whole thing because then I have to make dotted lines out of it. What you can see is that it's coming out further this way in the XY plane. This point's in the XY plane, this point's in the XY plane. And what you're getting is this point to this point to this point. So hyperbola is opening like so. You then get if I move up this far, get a point here. I get a point here, get a point down here, and you get a little bigger by point. Comes like this. Then you get the third one here. Comes out like those, and sketches are great. It could be better shaded. But you also get hyperbolas in the Wising, playing parallel to the Wising. So you can get a hyperbola here, a hyperbola back there. And if you do it carefully in a series of planes on a well-chosen axis, you begin to see how the ellipses and hyperbolas articulate. Okay. Now, think a little bit on that idea. I can do a little bit more of that next time. Okay. I can do an ellipsoid, which is a little easier to draw and a little easier to see. Okay. Now, I do want to move on, talk about chapter 4, but first, I have no idea whether that was in focus or not. It sure isn't right now. It was when I focused it. Okay. Again, I'm going to ask if you have any questions on chapters 1 and 2. Okay, chapter 4 is on vector valued functions in general, where the function is a function of positioning space. So example. Very simple example. You could eliminate one of the variables. Well, let's talk about that. Given a value of x except 4, right? Given a value of y greater than or equal to -2, we get a vector. So for example, at the point 5, 1, what is f of x, y equal to? Well, if we plug in 5 for x, we get 1 over 1, which is just 1, which is going to give us I, right? And plug in 1 for y, we get the square root of 3. Okay, so what's that look like? Well, it's a vector. It's like 1 unit in this direction, 1.7 units in this direction. So it's going to be a vector. So here's a 0.51. This vector is f of 5, 1. Okay. Now, if we let x equals 5 and y equals 0, well, that's going to get us at 0.50. And the vector is going to just be I. Now, does everybody have differential equations? Everybody have? Okay, you did direction fields, right? So you're kind of familiar with this idea. I want to draw a direction field. Well, this gives me a direction. It actually gives me a vector field, which is not just direction, but actual vectors, some of which are longer than others, right? So if I go up to down to let's look at something else. This vector is more like this. If x is 0, then you have square root of 2j. So it's I plus the square root of 2j. And then 5, -1, it's I plus j. So, yeah, f 5, -2 is just I. Just like this vector field is going in this direction, and this direction, this direction, this direction. The vectors actually get a bit longer. And as you go up, the I component stays the same. You got just plain old I, but you're adding a bigger multiple of j, right? Makes sense. And then let's say we go along this line where y equals 1. If y equals 1, then this vertical component is always going to be square root of 3. The horizontal component, as we move to the left, x gets less and less. So like here's x equals 4. Here's a line x equals 3. Here's a line x equals 2. I'm not to good scale here, but you get the idea. Okay, the j component is always 1. That's always square root of 3. If I go to x equals 3, I have 1 over, sorry. Okay, at x equals 4, I get nothing, right? Okay. I go to x equals 3, and the I component becomes -1. So that now the vectors are going this way and this way. And so now I don't want to draw a bunch of them. I just want to get the idea that there is a vector field here. There's a pattern to it. And there are often ways to find the pattern that are easier than just plotting a bunch of points in a grid. And we'll talk about some of that. Okay. However, in this case, plotting along horizontal or vertical lines would give you a good picture if you start thinking through how the patterns are emerging, because the j component depends only on y, the I component depends only on x. And if you had x's and y's mixed up in these things, it could get pretty complicated. Yeah, go from there. Now, you can get the domain and the range. N equal 4, y is greater than -2, right? So what you can do is you can come down here to find y equals -2. all this stuff down here is excluded from the domain, right? And then you also exclude this vertical line where x equals 4. So this leaves you this chord of a plane and this chord. Does that make sense? So the function is only defined in these quarters. Another thing you can see is that as x approaches 4, this reciprocal is going to get very big. Either positive or negative because your denominator is approaching 0. So that the x components would rapidly grow between here and here. The vectors become almost horizontal and they stick through the vectors you've already drawn, which is makes it complicated to draw this thing. Okay, that's something similar happens in this slide. It's vectors. Okay, well, you can take it apart and look at how these functions behave, but mainly we want to talk at the beginning about like the domain, which I've already talked about last time. Okay, just look for square roots and look for reciprocal, look for zeros in the denominator. And if you have a function that isn't defined somewhere, some other kind of function, be careful of that. Okay, like for example, you've got a tangent function. If your tangent function isn't defined, is x equals pi over 2. Okay, sine over cosine, cosine 0. So you divide the plane up into a bunch of regions with pi, negative pi over 2, pi over 2, pi over 2, so forth. All that is pretty much common sense. You want your function to be defined. And it's usually pretty easy to see where it is if you think about it. And you do want to think about it. Okay. These are vector value functions. Use your vector fields. Just plain old scalar value functions of position might be like f of x, y. No I, no j. And so we're going to do these before we do these vector fields, these vector value functions. I wanted to mention this to give you a little bit of context for this. Okay, this is important in itself. Okay. What's a domain? X, y has to be greater than or equal to 4, right? Gives you y is greater than or equal to 4 over x. Okay, it's just vertically stretch reciprocal function by factor 4. So at some point over here, you got the point. And reflection of that point. Be negative, one negative. Just put a scale on this. Y has to be greater than the value you get on this function, which means that your domain be like here. And then to the left of the y-axis, you have the numbers above this reciprocal curve. Now, why does it work where this thing isn't symmetric? This domain isn't symmetric. Think about the numbers. Let's take a number over here, like the point negative 1, 1. Okay. Well, the value there, so the domain is like this. Because clearly, y equals 0 would be part of what I shaded here, wouldn't it? And if y is 0, you got square root of negative 4. Oh, yeah. To erase this shading and explain this. Y is greater or equal to 4 over x if x is greater than 0. Because then you're dividing both sides by a positive, right? Okay. And y is less than or equal to 4 over x. Oh. Okay, x is negative on this side of the axis, so when you divide by x, you're dividing by a negative number. No, it is. So what I did there was kind of dumb, I know better. Okay, so there we have it. You understand that that would then be a depiction of the domain of the function. And it doesn't extend to where x equals 0, the y-axis, because this reciprocal curve never gets to the y-axis. Okay, so we've got a question. A little more articulate explanation. The question was, well, before we parameterize x and y, so we get a curve, okay? Well, yeah, if you parameterize x and y in terms of t, you do get a curve. But that then restricts this function to that curve. And even more specifically, to the part of that curve that's in the domain of this function. So if you do cosine of t, if you do x equals 6 cosine t, y equals 6 sine t, so you get a circle of radius 6, that clearly intersects both of these domains. So you got part of that curve going through the domain here and part of it that's going through the domain here. And you could do things with that curve, and we do. Okay. So if you're looking at what happens to the values of this function within a specific curve, we could sketch this function, attempt to sketch this function in 3 dimensions. So you would get a surface and you'd have this curve in the XY plane. And above that curve, you would have a curve on the surface. Now we're going to see that, so I don't want to anticipate that too much. But then you can find, directional derivatives, the rate at which the function changes on a curve. Okay. We do partial derivatives, which we're going to do. We'll talk about partial derivatives. Pretty simple. Now, what you do with them after you define them and learn to calculate them, which is easy enough, it gets more complicated. So, without going far into that, this is an example of a scalar function with a domain. Okay. You have similar problems in the book. If it's a square of x squared minus y squared, well, then x squared minus y squared has to be greater than or equal to 0, which means x squared has to be greater than y squared. And then that's, you have the x equals y curve, and the x equals negative y curve. That splits the plane into 4 quadrants. And only 2 of those quadrants are in the domain. You do stuff like that. So I'm going to just kind of turn you loose on those problems. I don't think they'll give you much problem. It doesn't ask you what's the domain. It doesn't ask you to graph it. Okay. But where you can understand graph the domain, it's worth thinking about, because that becomes part of what we need to know. Okay. So there's also limits and continuity and so forth. Okay. So you have to deal with those ideas. And we dealt with that just a little bit before, but that comes in section 2. So all I'm going to do is sign section 1, make sure you're good with chapters 1 and 2. Okay. And then just work through the problems in section 1 and chapter 4. If you go down, way down to the bottom, there, very bottom of the assignments page, I think I have the assignments there. Okay. But then I pull them up by date, so you know what's doing which date. But as long as you know it's 4.1, if you want to look at that before I get it posted there in a little while. Okay.